Welcome to this explainer. Between classes, studying, and just trying to keep up with life, we rarely stop to think about the physical world holding everything together. Today, we're taking a quiet moment to step back and look at the invisible, engineered materials that literally shape our modern lives. If you've ever been curious about how the stuff around you actually works on a molecular level, well, you are definitely in the right place.
So I want you to take a second and really think about this. What could a spacecraft tearing through the atmosphere, a nonstick pan frying up your morning eggs, and the tires gripping the road on your daily commute possibly share? The answer isn't in what they do, but in what they're made of. They are all entirely made possible by the quiet, everyday marvels of advanced chemistry.
Okay, let's dive into this. We've got a pretty fascinating roadmap today. We'll start with the power of polymers, look at how we upgraded nature with vulcanized rubber, explore the engineering extremes of Teflon and PVC, check out the incredible strength of composites, and finally, wrap up with materials that literally have a memory.
All right, part 1. The power of polymers, or as I like to call them, are molecular building blocks.
At the absolute foundation of everything we're looking at today is the polymer. Now, the textbook definition is that they're high molecular weight organic compounds. But what does that actually mean for us? Just picture incredibly long, coiled molecular chains. They're almost like tiny microscopic springs. When you pull on them, these chains uncoil and stretch out, giving the material its elasticity. And when you let go, they snap right back into that coiled helix shape. This one simple ability to stretch and return is the fundamental building block for practically everything we're about to discuss.
Moving on to part 2, where we talk about upgrading nature, taking rubber from sticky to strong. So here's the problem. Raw natural rubber, or polyisoprene, is actually pretty weak. It gets sticky when it's hot and brittle when it's cold. To fix this, engineers came up with vulcanization. It's such an elegant process. First, you take that raw natural rubber and you mix in sulfur. Then, the real magic happens when you heat that mixture in a mold to somewhere between 100 and 140 degrees Celsius. During this heating phase, the sulfur does something absolutely crucial. It acts as a bridge, linking those loose, floating polymer chains together. And this brilliantly illustrates exactly what's happening. See how the sulfur atoms step in as structural cross-bracing? They literally tie those wobbly, independent chains together into a solid network. By locking the chains in place, the rubber goes from being a sticky, weak mess into something incredibly durable, highly elastic, and totally heat-resistant. It's a total game changer. When we zoom out, we can see how this structural upgrade solves huge problems, especially with synthetic rubbers. Let's look at a few you probably rely on every day. Take Buna-S rubber. It has incredible abrasion resistance, which makes it the absolute perfect material for the heavy-duty tires on your car. Then there's Butyl rubber. It's exceptionally airtight, so we use it for inner tubes in tires or anything that needs to hold pressure. And finally, Thiokol rubber. This one laughs in the face of harsh solvents, making it the go-to choice for things like chemical hoses and engine seals. Just think about that. A few simple molecular tweaks, and we get materials perfectly engineered for massive real-world impact.
Okay, part 3, engineering extremes, focusing on Teflon and PVC. These are plastics built for literally every environment.
Let's take polyvinyl chloride, good old PVC. Now, pure, unplasticized PVC is super rigid and chemically inert. It's built to take a beating, which is why it's used for hard safety helmets and tough plumbing pipes. But here is the wild part. If you just uniformly mix in an additive called a plasticizer, like dibutyl phthalate, the whole material transforms. Suddenly, that hard pipe material becomes the flexible, waterproof fabric you wear as a raincoat or use for electrical cable insulation. It's literally one base material, but two completely different physical realities, all because of a single additive.
Now, what's really interesting about this number right here, 350 degrees Celsius, is that it is the exceptionally high melting point of another famous polymer we all know, polytetrafluoroethylene, but you probably just call it Teflon.
The secret behind Teflon's insane heat resistance comes down to its highly electronegative fluorine atoms. Basically, these atoms hold onto each other with incredibly strong attractive forces. This makes Teflon almost perfectly chemically inert, meaning it flat out refuses to interact or bond with other substances. And that right there is exactly why it's used for high-temperature gaskets and engines, and of course, why your morning pancakes slide right off your nonstick pan without leaving a mess.
Moving right along to part 4, the strength of composites, or what happens when materials combine their forces.
Sometimes a single material just isn't quite enough for the job, so we make them team up.
This is the whole idea behind fiber-reinforced plastics, or FRPs. You're basically blending two things. First, you've got super strong, stiff fibers, like glass or carbon. Second, you surround them with a polymer matrix. It's perfect teamwork. The fibers provide all the raw, structural muscle to prevent cracking, while the matrix wraps around them, distributing the weight evenly and shielding those vulnerable fibers from the elements.
By combining forces like this, you unlock superpowers that neither material could ever pull off alone. FRPs give us structures that can absorb massive shocks while remaining unbelievably lightweight. That's why engineers rely on them for the most demanding environments imaginable. We're talking spacecraft components, super sleek boat hulls, harsh acid storage tanks, and high-performance car parts.
And that brings us to our fifth and final section, materials with a memory. Welcome to the smart future. This is where things start to feel a bit like science fiction. We're talking about shape memory materials. The idea is mind-bending. These are smart materials that you can severely deform, crush them, twist them, whatever, but they actually remember their original programmed shape. And when they're exposed to a specific trigger, which is usually just a change in heat, they snap right back to normal.
So the crucial point is how this phase shifting actually happens deep down in the structure. It all hinges on two very different crystalline states. When the material is cool, it sits in what's called the martensite phase. In this state, it's pretty weak and super easy to bend. But the moment you heat it up, the internal structure transforms into the austenite phase. This phase is much stronger, and it physically forces the material to snap violently back to its original programmed shape.
Let's walk through how this looks in a practical cycle. First, you set the permanent shape while the material is blazing hot. Then you let it cool down into that weaker, flexible state. Now you can crush it, fold it up, or tie it in a knot, and it'll just stay like that. But watch what happens next. The instant you apply heat again, the crystalline structure wakes up, shifts, and the material perfectly recovers its original shape, as if nothing ever happened.
Actually, here's a quick fun detour for you. One of the most famous of these smart materials is a nickel-titanium alloy called nitinol. The name is actually an acronym standing for the Nickel-Titanium Naval Ordnance Laboratory, which is exactly where it was discovered. It's kind of wild to think about how many of the everyday materials we take for granted actually started out as top-secret military research.
The real-world applications for this are just incredible. For example, look at the jagged chevrons on the back of modern aircraft engines. Those are made of shape memory alloys that physically change shape depending on the temperature during flight to optimize airflow and drastically reduce engine noise. Or take robotics. Engineers use these materials as artificial muscle wires. Because they contract and expand with heat, they perfectly mimic the smooth, pulling motions of human tendons.
And the tech isn't just limited to metals anymore. We've got shape memory polymers now, too. These are out of this world. We use them for deployable spacecraft antennas that are crushed down tiny to fit inside a rocket and then automatically unfold themselves in the heat of the sun. We're even putting them into clothing that changes its weave based on your body heat. In medicine, they're absolute lifesavers. Doctors use them as minimally invasive stents. They're inserted into an artery while packed up small and then gracefully expand to the perfect, life-saving size once warmed by the patient's blood.
To really sum this all up, this quote hits the nail on the head. These materials have completely infiltrated virtually every cutting-edge industry on the planet. Aerospace, civil engineering, microelectronics, textiles, you name it. Engineered materials truly are the unsung heroes of modern innovation. They quietly hold our world together, and sometimes they even adapt to it.
As we continue to program memory into the very molecules around us, what impossible structures will materials engineers invent next? The big practical takeaway here is that our physical world isn't just a collection of dead, static objects. It's an ongoing, adaptable conversation happening right at the molecular level. Next time you grip your steering wheel or fry an egg on a nonstick pan, just take a second to appreciate the quiet, beautiful engineering making it all possible. Thanks so much for taking this calm journey through the microscopic world with me today. Take care of yourselves and keep learning.